Hello everyone, this is Sohail. I'm going to talk about our work in Pragmatic learning-based congestion control for the internet, which is a collaboration with Jenny and Jonathan at MIT. These days, we are observing a kind of tug of war among learning-based approaches and classic heuristic designs, in particular in the context of congestion control. So to set the context and elaborate on our key design decisions, let's look at these two key questions. First, let's see why using learning-based approaches in the context of congestion control might be a good idea. To answer that, we need to look at the history of this topic. Throughout all these years, a lot of things have changed, from network technology to user demands. But at least one thing is not changed, and that is having a lot of different congestion control schemes out there on a yearly basis. So the fact that we do have all of these schemes out there is a bit alarming because if we had a few good ones that can adapt to future technologies or different environments, we wouldn't have a lot of them out there. And that is the issue. We still lack adaptive frameworks. That's exactly where learning-based approaches can come to the play because these approaches have great potentials to bring adaptiveness to the system. Now let's see why using learning-based congestion control might not be a good idea. To that end, we performed two simple experiments. In the first one, we brought up a network similar to the one shown here with 20 millisecond minimum round trip time. What we did was changing the capacity of downlink in a stepwise manner every 10 seconds, meaning 500 times more than the minimum round trip time of the system. And that is clearly enough time for any congestion control to converge. So now let's see how current learning-based congestion controls perform in this unseen network. And as you clearly can see here, we do have serious performance problem. So the bottom line here is it seems that using learning-based congestion controls in unseen network scenarios faces serious problems. And of course, that's not a good news. The other experiment is done by using a 50 megabit per second link and sending traffic over that for about 2 minutes. What we gather here is CPU utilization at the sender side. To give you a base, I'm showing you here the overhead of TCP cubic, which is a classic heuristic and default TCP scheme in most of today's platforms. Now let's look at the current congestion controls using learning-based approaches. And clearly you see we have a problem. This time it's about the overhead. Putting all together, you see that we have a confrontation between modern approaches and classic approaches. Even if you look at the learning-based designs model, you can see that they would like to be revolutionary approaches replacing classic heuristic designs. In contrast, in this work, we would like to do something else. First, the revolutionary aspect of design is not really an interesting thing for us. Instead, we would like to be a pragmatic approach. And by that, we're not necessarily trying to replace anyone. The key for us is to have the best of both worlds. So if that means collaborating with them, why not? On that note, we have a two-level control hierarchy. In a coarse-grained manner, we use a deep reinforcement learning block to perform periodic actions. In parallel with that, we have a fine-grained control using classic heuristics, which happen to be per acknowledgement. The fundamental thing in this architecture is that we'll try to have dynamics of heuristic systems at the same time of having adaptiveness of learning-based designs. Here is the big picture of Orca. We do have a classic heuristic, as I said, doing its job. But in addition to that, we do have a monitoring block already implemented kernel, collecting information from network and control buffer. Then it generates some digestible states useful for the other blocks there. One of the other blocks is reward generator block, which basically looks at the observations and then associates the so-called reward to current observations. And the key thing for this reward is to motivate the agent toward minimizing delay of the packets while maximizing delivery rate and minimizing loss of traffic. And then all these inputs will go to the agent and it basically tries to come up with a better congestion window for the system. Now let's look at the under the hood of Orca and see how it really works, but in a more qualitatively manner. Here we do have a scenario in which we suddenly drop the capacity and would like to see how system reacts to that. Clearly, these two pictures show that we have two problems. First, of course, because of the drop of capacity, we have less delivery rate. And the other one is we have sudden jump in the delay of the system because we have sudden jump in the queuing delay of the system. Both of these are in the direction of getting lower reward. So these things will push the system toward a reducing congestion window as shown here. But to see how exactly the system does it, we need to zoom in here. The classic heuristic tries to probe for more bandwidth by increasing congestion window. But the agent learned to control that behavior by reducing congestion window. Again, classic part tries to probe for more bandwidth, but this time we have sudden drop of the capacity there, which means we have lower rewards, and this makes the agent to push the congestion window to a lower value. And this happens again and again, and then we do have, at the end of the day, this downward trend. In the other scenario, we do the opposite. We suddenly increase the capacity of line to see again how system reacts to that. Clearly, this time we will have better delivery rate without compromising the delay of the system, which means we get higher reward, and because of that, the congestion window should go higher. But again, let's zoom in to see what happens. The classic part tries to probe for more bandwidth. The agent again tries to control it, but this time, because we have sudden jump in the current capacity of the link, the probing mechanism of classic heuristic basically helps the system to reveal more available bandwidth. And this happens again and again, and then at the end of the day, we do have this upward trend there. Now let's see how Orca performs in the two experiments that I mentioned earlier in this talk. In terms of the overhead, you can clearly see here that Orca's overhead is much lower than the other landing-based designs. And we would have expected that because we do have a partner doing some part of the job, and that partner happens to be a low overhead partner. In terms of the unseen scenarios and the step scenario that I mentioned, you can clearly see in this picture that Orca has way better dynamics compared to the other landing-based designs. And I already described, of course, the reasons why it happens. To train Orca, we use TCP cubic as the classic heuristic block. And we trained the system for about 6 hours over a small set of single bottleneck links. To give you a better picture of its performance during the training, we also designed a clean slate counterpart, which is basically Orca without the classic heuristic block. Here are the results during the training. You can see that the clean slate can achieve up to the score of 20 during the training. But if you look at the Orca's results, you can clearly see that we have 3 times better performance compared to the clean slate design. And that is in part because of that two-level architecture that I already described. Now let's see performance of Orca in the internet. We have examined Orca's performance in various scenarios in the internet, and here I'm sharing with you results of one of those experiments called the intracontinental scenario. Of course, you can check out paper for more scenarios and results. In this scenario, we brought up different servers around the US and sent traffic among them using different congestion control schemes to compare the performance of those schemes with each other. This graph shows the average normalized results. X-axis is end-to-end delay, and Y-axis is throughput or delivery rate of the system. And the best operation point in this graph would be top right side of the graph. Now let's see how Orca does its job compared to the others. And here it is. To conclude this presentation, let me point out a simple note here that we hope promising results of Orca can convince you that using modern landing-based techniques does not necessarily mean we need to put aside more than 3 decades of active research in this topic. And with that, I'm happy to take questions.
Hey, Sohail. Seems like they want us to wrap up soon. Sohail, great work. I'm going to read out some questions. The first question is coming from Tong Meng. And Tong is curious if the performance of Orca would change significantly with a different reward function. or if it considers different performance metrics?
Yeah, actually, that's a good question. The reward function is kind of part of the system, if you like. If you change it, of course, the behavior of the system completely changes. Yeah, so that's basically the core of the whole thing.
Perfect. There's another question from Kaustubh Jan, and Kaustubh is curious, how does Orca perform in wireless scenarios with bandwidth variation at much smaller time scales?
Yeah, actually, we have some performance in the cellular scenario, which happen to have higher even fluctuations. So yeah, you can check out the paper for that, which basically show that it does a good job still the cellular network does, but not in a wireless. So we haven't tested the Wi-Fi scenario basically.
Good. The last question is from Maria. Maria is curious if you could comment on how fair Orca is to other TCP versions.
Yeah, we do have also results of TCP friendliness and of course fairness itself. In the paper we show that we have both properties.
Thank you, Sohail. That was great talk. I had a quick question about sort of the overhead graph that you had. So how are you quantifying overhead? Like
CPU utilization, we counted that as the overhead system.
Okay, so basically like, okay. And another little question I had was, so in my mind, like REMI is also in some sense combining like classical heuristics with machine learning in the sense that it's just learning the parameters and like the sort of classical heuristics are what sort of determine like AIMD and so on. So
yeah, go ahead.
Yeah. So like in the sense like philosophically, like how would you sort of treat REMI in comparison to Orca? Like
basically, REMI does not stand on top of the heuristics. Let's say REMI's philosophy is to basically go and have a kind of brute force manner to figure out in the entire space what would be the best actions possible. Sort of going through a decision tree. And try to figure out in the entire space what would happen. And we also compared with the REMI in terms of the performance. What we observed was REMI in the real scenarios like internet, intracontinental and intercontinental, actually does a very bad job. So in terms of the throughput, it cannot do a very good job basically.
Okay. So one question we have on Slack is there are so many congestion control methods. Can Orca fit the situation of data centers and work as well as congestion control dedicated to data centers?
Good question. The very fundamental thing about Orca is it's not a scheme, it's a framework. So basically you can have a customized version of that for your certain environment. But what we did in this paper was we focused on the internet version of the Orca, let's say, and we trained sort of our Orca playing on the internet. So you can imagine that if you're interested in having a very customized version of the Orca, you can have it, trained over your own network, and even you can use, other heuristics which work better in your network. You might, end up to using DCTSP instead of the cubic. So the choice of cubic, for instance, for us was because of some, properties that cubic does, fairness, friendliness, those sort of properties in the internet.
Another question is, it seems that you only optimize throughput. First of all, is that true? And if so, what about latency and stability under network dynamics?
Actually, we optimize so-called power in the network, which means throughput over delay. We basically minimize delay while we are maximizing throughput. That becomes, the objective.